Hello Physical Science, this is Mr. B, and we're going to finally wrap up section 1 today, a very long section, talking about the actual structure now of an ionic bond, so what they actually look like, because up to this point we've talked about the electron dot diagrams, which show us the number of valence electrons, that will show us which atoms are more likely to react with one another, what happens when one atom transfers another atom, and how that leaves us with positively charged or negatively charged ions. We have to write the symbols next to them. And then we talked about how we actually write the formulas with just a little subscript number that kind of gives us the relative, or that kind of gives us the idea, kind of a ratio of the number of atoms present within the compound. So now we're going to talk about what an ionic compound actually looks like and kind of how it affects its properties. So this slide was mentioned at the beginning of the last video, but it doesn't really come into effect until now, so I just decided to put it on there again as a reminder. So it says again, how does the structure of an ionic compound affect its properties? So it's solids whose particles are arranged in a lattice structure are called crystals, and the properties of an ionic compound can be explained by the strong attraction among ions within a crystal lattice. So again, last time I told you just to kind of hold on to that bit and piece of information because we'd explain it more, and that's what we're going to do right now. So we talked about chemical formulas last time. So a chemical formula for an ionic compound tells you the ratio of the ions in the compound. So remember, we had magnesium, so we had Mg, and then so magnesium had to give 2 electrons up, 1 to each chlorine atom, so we had MgCl2, but it does not tell you how those ions are actually arranged. So how are they actually attached to one another? What does the actual compound physically look like? So if you looked at a sample of sodium chloride with a hand lens or microscope, you would be able to see that the pieces of salt are shaped like actual cubes. And so we're going to see here in a second how that, or why that is the case. So the crystal shape is a clue to how the sodium and chloride ions are arranged in the compound. So because salt, again that's what salt is, because it's arranged in a cube form, that is because of how the atoms attach to one another at the very smallest level. So ions in sodium chloride are arranged in an orderly three-dimensional structure. So each chloride ion is surrounded by 6 sodium ions, and each sodium ion is surrounded by 6 chloride ions. So that's going to make a really orderly arrangement that we'll see here in a second. And each ion is then attracted to all the neighboring ions with an opposite charge. So you're going to see we have basically all negative ions are surrounded by positive, so all negative ions are surrounded by positive ions, and all positive ions are surrounded by negative ions. So that's going to make a really strong structure here. So this set of attractions keep the ions in fixed position in a rigid framework or a lattice. So this word has been mentioned before with a crystal lattice. So this just means that the ions are in a fixed position in a rigid framework. So I'd make sure you wrote down what lattice means. So it just means that the ions are in a fixed position in a rigid framework. Rigid framework and lattice are associated directly with one another. So what this is actually telling us is right here. So this is the structure of the ionic compound and how it relates to its actual physical shape. So here we have a chlorine or chloride ion. Here we have our sodium ion represented in orange, and you can see that they're all interspaced out with one another, each positive or each negative. So look here in the negative chlorine, we have 1, 2, 3, 4, and we probably have one more 5 below it. And then right here with our sodium, it is surrounded by all negative charges. So all positive and negative charges are equally distributed out between one another, and that gives us this cube shape. And then over here, this is the actual shape of sodium chloride. So it is shaped like a cube. On the molecular, the atomic level, it's shaped like a cube, and on its physical, eye level, visible level, it is shaped like a cube as well. So the shape of an ion at its lowest level is directly related to the shape of the ionic compound. So that's pretty cool, I think. We can actually see that the arrangement of atoms affects its actual physical arrangement. So shaped like a cube here, so therefore it's shaped like a cube over here on the right. So that's pretty cool. So the shape of an ionic crystal, for example, the cubic shape of a sodium chloride crystal, depends on the arrangement of ions in its lattice, which I just said. So the arrangement of the ions depends on the ratio of ions and their relative sizes. Crystals are classified into groups based on the shape of their crystals. So that's, if you're shaped like a cube, you're going to be in one group. If you have a different shape, you will be classified in another group. And the properties of sodium chloride are typical of ionic compounds. So they have a high melting point. It's a poor conductor of electric current when melted, or so when it's a solid, it's a poor conductor. When it's melted, it's a good conductor of electric current. And then its crystals shatter when they're struck with a hammer, and that kind of means it's a little more brittle. And what happens when you actually do strike it with a hammer? This is pretty cool. So when an ionic crystal is struck, ions are moved from their fixed positions. So you hit it with the hammer, this is going to cause these negative ions, or this top row here, to be shifted down. Then ions with the same charge then repel one another, and the crystal will shatter. So there is an actual atomic reason. So we smash it, the force from us hitting it will cause these to actually shift down and to move from their position, and then now we're going to have negatives next to negatives, positives next to positives, and they don't like that, so they're going to repel from one another, and that is actually going to cause the crystal to shatter, which I think is pretty interesting. So that is it finally for section 1. That was a long section, but a lot of good information in there, so let me know if you have any questions.